Let me introduce myself. I'm Sam van Roosnel, Communication Manager this year at Solar Boat Twente. And later today you'll be met by Camille Postema and Jitse Boonstra, who are on the couch right now. And they will explain you something about our hydrofoil system. But more about that later. This year, Solar Boat Twente exists of 18 people. 18 different motivated students, each and every one from the University of Twente this year. What do? We build a boat that's powered by solar energy. Kind of obvious if you see Solar Boat Twente, but it's not that obvious when you think about it. How everything works, I will go into that a bit later. It's about solar energy, and we like to compete in races with it. So, first of all, our motto. We don't only build the boat to race, we also build the boat to inspire, which gets to our motto, which is innovation to inspire the maritime sector. More about it later. In short, the maritime sector as it is right now, just number-wise with all the gases, it's not too good. So what we like to do, we not only have this beautiful, amazing project behind me, where we build a high-tech boat, we also want to use the platform that we create with the boat to inspire the maritime sector. So that's our motto. To reach that, we have a few goals. First of all, we want to foil. With foiling, we mean flying just ever so slightly above the water to increase our speed. If we foil, we want to win. We want to win races. It's an easy thing to say that we want to build the most efficient boat in the world. It's a harder thing to actually prove that we have the most efficient boat in the world. To prove it, we compete in races such as the Dutch Championships in Akron or the World Championships in Monaco. Next, we have to network. As I said, we want to inspire people. To inspire as much people as possible, we need to reach as much people as possible. So networking is an important part too. And the last step, of course, is to inspire each and every one that we meet. Yes.
Can I ask questions?
Yes, of course. Yeah.
What do you stand right now in competition?
That's actually difficult to say. Last year and the year before, there wasn't too much races because of COVID, of course. They did compete in Monaco, which didn't went too well because the boat had some technical failures. So to look at where we are in competition, we can't really tell right now. Theoretically, we have a good chance to end up on the podium. In practice, we'll see in May when we have the first race.
TUE and TU Delft?
Yes, so Eindhoven doesn't have a boat team. They have a lot of student teams, but not a solo boat team. Delft has one, or had one, I have to say, because they switched 2 or 3 years ago to hydrogen. So we mostly learn from them, they mostly learn from us, but we're not really competitors anymore because they switched. Then there's a few hogescholen, I don't know the word in English, that also have a few teams, and then there's a few hobby teams and a few engineering teams where there's actually some engineering companies that just put a few engineers from the company to work with the boats. If that answers the question. Okay, good. So first of all, foiling. This is a picture from the test ride earlier in our year. It was, I believe, the beginning of November in 2021. And I think it shows really well what we mean with foiling, because you can see in the back at the boat we have a few struts, 2 in the front, 1 in the back. And when we reach a certain speed, the boat, the hull of the boat lifts just ever so slightly out of the water. When doing that, the boys will explain everything about it. later, but when doing that, your drag, the water drag and resistance decreases that much that you can go to insanely high speeds. In short, it's really important for us to be able to foil and to be able to have a good system for foiling in order to actually stand a chance at the competitions. Second of all, winning. Of course, Monaco, our final competition. In solar boat racing, there is a few different race elements. For example, you have the endurance one, which is the endurance race, which is the one that we focus on most, which is a race that, depending on the location, depending on the day, is either 3 to 5 hours of constant driving, and just like the 24 hours at Le Mans, the person that has the most amount of kilometers on the same course wins. So it's basically, you have 3 hours, the one that comes the furthest wins. You have a sprint race, which is a stretch of a few hundred meters. The one with the highest top speed wins. You have a match race where there's two boats competing against each other, completing the same track.
The question, what do you consider high speed?
What we consider high speed? As of now, I believe the current world champion has a top speed that they ever reached of just above 50 kilometers per hour. And as they're the world champion, I believe I can say that's pretty fast. Yeah.
So what speed does the boat come out of the water? 18 foils can lift the boat out of the water. 22 can stabilize.
Yes, so for the people at home, 18 out of the water, and then at 22 we stabilize.
Hit 22 kilometers, starts coming up.
Yes.
Because you need, the more speed you have, the more control you have. Because higher lift forces you can mediate with that more.
Yeah.
Yeah, but we'll discuss it.
Yeah. So here's some more pictures of Monaco. We'd love to show this one, because this is the point where we're actually in front of the current world champion. The picture on the right, there in front. So no, but this is an example of the match race where two boats complete the same course. It's often two circles, so one smaller circle and a bigger circle. One boat goes to smaller circle, the other goes to bigger circle, so you don't crash into each other, because that doesn't help anyone in the end. But the other part of Monaco, and I think that really shows for the culture inside of solar boat racing, is the tech talks. Whenever you have a solar boat race and the boat breaks down, as soon as the boat is out of the water, everyone stands around the bonnet to find the problem together, and we'll fix it together. And that shows in Monaco as well with the tech talk, where every team has its own subject to talk about. And a few years ago, we actually won that competition with the best tech talk, when they talked about the propulsion system that they designed that year. So I think that also shows the common goal, again, to inspire the maritime sector, also with the other teams and with the sport itself, that we're not only there to have a good time and to build just crazy things like the boat behind me. We actually want to change something within the sector. We actually want to improve some things in the world. Next up, networking. As I said, we need our network not only to fund the project, not only to produce certain parts. For example, the wings that Camille and Jitse will talk about in a bit, we can't produce them in-house, so we have a partner for that who helps us with the production in that. But also our network with students is really important, because not only is it one of the main selling points for partners, of course, that they want to be in contact with our students and with the students at University of Twente and Saxion. The students themselves are also really important to spread the word of Solar Boat. if they start talking about us to their friends, and their friends will start talking about us to their friends, there's more and more people who will hear our story, and maybe eventually we actually change a bit in the maritime industry. Speaking of which, the last step is inspire. We hope that in the future, at least the private sector within boat life will look somewhat like that. So this is not a project that we are involved in, but somewhere in Turkey there's this yacht that's entirely solar powered. We want to see more things like that. As I said, when you look at the numbers right now, there's about 2.5% of all CO2 gases is from the maritime sector. Doesn't sound like much, but it is a lot. We're not the biggest transport sector yet, but we're getting there, and this is not a competition that you want to win. This is mostly caused by big container traffic, so that's not something that you can attack with solar boats yet, because the solar panels are the technology for that is just not that far enough. But we can change something, for example, with the more private, the more commercial side of the maritime sector. So that's what we're striving towards, and we actually do have a few companies within our network that are already busy improving in the sector, and they actually asked for our help. So that's also a nice part of Solar Boat, is you actually get to be a part of the industry itself. Yes, so about the boat. The boat can be described in 4 different parts. We have 5 technical sub-teams. We can describe it in 4 more physical parts. First of all, the hydrofoils, which are needed to fly, of course. I'll skip on that for now, because we have Jits and Camille who will explain everything way more detailed than I could ever wish for to know. Then we have the propulsion, which is basically anything from the motor towards the propellers. We have the structural team, and I skipped that one. I'm so sorry. The structural team who are mainly responsible for the hull of the boat, and right now they're working on a cockpit. And finally electronics, which is they are busy with every electronical component in the boat. So for propulsion, their biggest part of work this year is the back strut. We actually got it in last week. You can see on the screen there's a render of the back strut. It consists of different components, and I think it also shows what propulsion actually is, because you go from the motor up here with another steering disc down there, and the back strut itself. There's some gears. There's an entire gearbox to get the torque from the engine into the propellers, and then the propellers themselves. They basically did everything in this picture themselves. So there's no store-bought parts here. Just everything they make themselves. So even the propellers, there's a huge MATLAB script that they use to. No, it's not. No, yeah, it's a fixed one. So what they do, and that's actually something I wanted to talk about now. They have a counter-rotating propeller this year. So if you look below the boat right now, there's a single propeller. They actually have a double propeller right now, which means that the first propeller actually creates the lift to go forward, but it also has a bit of turbulence, and then you can calculate that turbulence and make another propeller that spins the other direction to count for the turbulence that you just made. So I think that's one of the more genius things that they did this year to develop that.
On the same shaft.
On the same shaft. So it's a bit small in the picture, but if you look closely, the shaft.
So there is a hollow shaft in which another shaft.
Yeah, but it's one shaft with two parts.
Yeah. So what you have one shaft that goes down. There's a a gear below that, and then there's one gear in the front that of course goes in one direction. But if you have on the same gear but on the other side, it spins the other direction. So you have, as Jitse said, you have one hollow shaft with the other propeller going through it. So in that way, with just one gear from the top, you can spin 2 different propellers. Yes, so the propeller is pointing forward, so it basically pulls the boat through the water instead of pushes the boat. And this is because that is more efficient in the end. Sorry?
It reduces the drag.
Yes. So because you have this thing right here, it's called the nacelle. That's just a big volume within the water, of course. So whenever the water hits that, you lose a lot of speed. If you have that in front of the propeller, you actually lose speed to increase the speed. And if you make sure that you have the increasing of the speed of the water before that nacelle, it actually results in less loss. I believe that's almost like Camille just said it earlier, so I hope I said it well. So that's it for the propulsion system. Then we have the structural part. Like I said, they do a lot with the hull. However, this year we decided on keeping last year's hull because structurally speaking it was still pretty much intact, and it just takes a lot of time and a lot of money to make a new one. And the minor improvement that we would have done were that little that we decided on just keeping it. So what he's doing this year is making a new cockpit. He already designed a new steering wheel to make the driving of the boat a lot easier for the pilots. But now he's busy with the cockpit to have everything that needs to be in the cockpit, for example a fire extinguisher or a flagpole, just all at the ready, and make it way more safe for the driver to be in the boat. And as you can see, there's a pretty high wall up here with the cockpit, and that's just all splash protection because you just want to keep all the water outside of the boat, of course. It does sound like little work to do, but he's alone this year and he's working really hard, and it actually, there is more that comes with it than it sounds like with just the cockpit. But in the end, when it's here, when it works, it's a really big and important part of the boat that normally with a smaller team would have been overlooked, as you might notice with the white, arts and crafts project. If this works, yes, good. Lastly, the electronics part. As I said, they do every bit of electronics in the boat. So they go from the solar panels to the battery. He's actually working on it right now. This is a picture of the battery just disassembled. We make our own battery. We buy the different cells and we then tack weld them together or spot weld them. Build our own battery management system. The solar panels, same thing. We buy the different cells separately, actually solder them together, and then they're laminated at a company also in the Netherlands with a nano coating. We had a lot of tiny prisms that trap the light just over the solar cells to have even more efficiency and less loss of light. Then there's a picture of the steering wheel. They don't build the actual steering wheel, they make the system that controls the steering wheel. So all the buttons, making the buttons work, making the communication with the rest of the boat work. And then lastly, there's a big part of the boat that you can't really see, which is the software part. Of course, every single component needs to be able to communicate with each other. So the software is a big part of it as well. I believe that's it for my part so far. And then I'd love to give the stage to Camille and Jitse.
Yes. Thank you, Sam. Are we loud and clear, by the way?
Yeah, cool. Well, this is Jitse, I'm Camille, and we'll go a bit more in depth with the hydrofoils. So let's start. Really nice picture. We like each other a lot. I have a background in mechanical engineering. Jitse has a background in applied physics, and both we are working on the hydrofoils. I'm on the mechanical side, and he works on the controls.
Yes.
So maybe it's nice to start from like, why do we want to fly? We already saw it a bit, but we want numbers, of course, because numbers are interesting. Well, we have the driving regime and the flying regime. There is a reason we call the people in our boat pilots. In the driving regime, we have the exact same drag for 15 kilometers an hour as for the flying regime at about 35 kilometers an hour, like 30-35, which is a huge difference. If you would have this plot and you would go further for the driving regime, you would hit 400 newtons at about 20 kilometers an hour. So the difference is quite a lot, and that's why we want to fly. But that's not the only reason. The other reason is as well to show the maritime industry the possibilities of maximizing this efficiency. The more we maximize this, the more people could be inspired by us and see, wow, maybe they did something in their backstrut or they did something in their wings which is really clever, and maybe it takes maybe 90% or maybe 10% better efficiency. And which is also nice to tell is that we work with an electronical system. Most people with hydrofoil boats work on a passive system that is used with floats. We also have those floats over here, but the difference is that those things are mechanically coupled. And because we do it electronically, we can adjust a lot more. Some of them are like passive even. The back strut or the back wing is just in a passive position, an angle of attack, where you can't do anything anymore. And now we, like at all speeds, we can defer with lift. We can say, okay, well, maybe our pitch gets a bit too high. We can adjust that just by a knob, which is really handy, of course. Well, let's talk a little bit about the lift model. Well, I think most of you are familiar with this, but we use airfoils under a certain angle of attack. And if you look a bit at the streamlines at the top and at the bottom, we'll get a pressure difference by Bernoulli, which is an approximation, but it's a nice case, a nice law to use over here. And because of this pressure difference and a certain area, we can lift things. And we only need really small wings in the water compared to planes, because the density is a lot higher for water. Well, maybe you can see what has this to do with a plane. Well, if we look at our boat, in fact our configuration is kind of a plane. The difference is that we use a really interesting configuration. Most of the planes have their center of gravity in front of their front wings, the central wings, and they produce downlift with their back wings. But because this is less efficient, we use like upper lift for all of the wings. And we place our two wings in front and one wing at the back. And therefore we have a canard configuration. Maybe it's a bit too detailed, but maybe some of you know it from aircraft engineering. But then inverse. So really interesting dynamics, but he will tell more about this.
Yes.
Any questions so far, by the way? Okay. This happens if we don't use controls. And at the moment as well, maybe I show it again, we don't have the back wing at it, so it's only lifting. As you may have noticed, it just falls down and it stops, which means we come into a stall. So it's just a passive control, it's just under a certain angle. Well, at that moment when you come up, you want to stabilize, so therefore you need a kind of a flap, or you need to stabilize the wing. Well, that's what we do. Maybe we can go further. How do we do that? Well, we have certain linear actuators at the top, which are also used in Mars rovers. They have can produce a lot of force, and are mostly strong enough to even bend or aluminum plates. So we have to be careful with that. That's put through our struts with a push-pull rod. So you can push and pull to a certain angle to your wing or to your flap. At the front we have flaps, which have an elastomer flap hinge, a living hinge over there, which makes it like that the flow goes over really smoothly without having a hinge with holes in between. And that adjusts the angle of attack of the flap or the wing at the back, but we'll have a look at it later. I'm a mechanical engineer. I like materials as well, so let's go a bit more in depth about it. We focused on getting it as lightweight as possible. A really interesting part I find is the PEG nacelle. PEG is a really interesting material, which is engineering plastic, chemical resistant, more than twice as light as aluminum, but as strong as aluminum. So I can also show you later on how light it is, but it is really light and strong at the same time. And it functions as both a structural part to hold the wings and also cope with all the bending stresses and all the compressive forces. But also it acts for a flow regulator. The flow goes around like a wing shape. So it has two purposes. Well, I already talked a bit about the living hinge. And what you can also see here is the aluminum L connector. The aluminum L connector connects the push-pull rod to the flap and follows the same shape as the strut again. So the nacelle and the L connector work both at the same time as a wing shape. And the nice thing to show about is the solid carbon laminated foil. We have actually 90 layers of carbon stacked onto each other in different orientations to make a really strong foil. Actually, you could stand on it. If you take two bricks, and you lay it on it, you can really stand on it and stamp on it. We don't want to do it, of course. We want to get it smooth, but in fact, you could do that. And only 3 of those things can lift our boat. Well, I find that really interesting, always. Well, other challenges we cope with. First, strength versus weight. Every year it's again the same question. What do we do? Do we want to go with more strength or do we want to look at the weight? A couple of years ago, our boat weighed about 144 kilograms, and last year it weighed 120. Well, a huge difference, of course, and maybe we'll get it even lighter. But if you make it lighter, you always have to look at, okay, do I have to put on a rib more over here, because you don't want to break things. Same goes for models versus empirical data. Of course, we use a lot of models. Also, we do CFDs for computer fluid dynamics for our wings, because we want to know how our things will cope with the flow and how efficient it is. And we also want to test that. And you will always see that the models that he uses will never be exactly the same as the real empirical data. So we always try to match those and try to adjust the model a little bit by bit, to get it more efficient, get it better. Yeah?
Do you use a program for your model? It's a mathematical model, but we implement it in MATLAB and Simulink.
Yeah, and also the simple flow simulations, we do that with X-foil. Maybe you know that. If it gets a bit more complex, if we also want to see the overall thing, we do CFDs at Van Oossanen, for instance. And what we also did is taking a bath with our boat at Marin, where you have a really long bath and your foil gets drained through or pulled through the water, and you have real empirical data instead of your CFD, which is also really nice. But that takes a lot of time.
A quick question on the hydrofoil. Is the length of the ship, is it relevant to the speed at all? Like a normal ship?
The length of the ship for speed?
Yeah, like a normal ship, you know, the longer the ship is, the more speed you can get.
Well, do we talk about hydrodynamics or aerodynamics? Because that makes a difference. If we have a look at aerodynamics, you want a really slender object. So really long object, no sharp edges. As you can see, that contradicts a little bit with our boat. Our boat is mainly looked at hydrodynamics, but that's something to go with for the coming years, to also look at the aerodynamics. So that's why we indeed also looked at a really slender boat. And also if you look at hydrodynamics, most of the more efficient boats are really slender and long and have an abrupt end.
Only looking at hydrodynamics, for controls it only matters where the center of mass is. So if you have a very long boat, it might be more in the front than it would be in the back.
Yeah. Also then stabilization is a bit different. Yeah, of course, in your pitch. Yeah.
Definitely.
Last thing, preventing water damage. Not something to, yeah, you had a question?
I have a question on stabilization from
Yeah.
a viewer online.
Mm-hmm.
He asked that when you're flying, you have to correct for the wave movement for the hydrofoils.
for the up and down movement, for example?
I think
Yes, we have had contact with a company who specializes in weather data, and they assured us that the amount of change that would come from the wave dynamics would not influence us that much yet.
So you don't have to correct for like the up and down movement from the wave?
As long as the waves don't touch the belly of the boat, it doesn't really matter.
exactly. Yeah. Last thing, water damage or linear actuators are unfortunately not watertight. So what happens if water comes through that hole for the push-pull rod and it hits the motor? Yeah, the motor doesn't like that. So both for the outside, for the struts and for the inside of the struts, we developed something this year. For the inside, as I showed a little bit already, we have membranes. We made membranes from TPU, flexible material. We 3D printed them ourselves. And it makes with another 3D printed shell that all the water that is coming in, all the splashes will be guided towards the sides. So none of that will reach the maximum motors anymore. As well, next to that we have the oversleeves. Yeah, you can see them over here. Really small. And it's flexible. And it can also extend a little bit. Yeah. And next to that we have the oversleeves, in Dutch manchettes, which are also used at sailing. And we put them to our boat with another 3D print, which makes a really solid and watertight connection between the boat and the struts. And we'll show that as well later on at our boat. Okay. Then Jits will take over.
Yes.
I have a question.
Yeah.
So when the boat is down,
Yeah.
you use the rudder for steering,
Mm-hmm.
Yes.
but you have two wings in front.
Yes.
Now with muff sailing,
Mm-hmm.
you also have one wing in front.
Mhm.
Yeah.
You can steer with your weight. Could you make one wing more inefficient so you can steer by using your weight?
It would be possible, but the motion of the pilot is quite limited.
Make one wing more inefficient to get the whole boat to tip over.
Oh yeah, of
the
course, we can decrease the lift of any wing at any time.
You already
Yeah.
use that.
Yeah.
We, for now, and which is also something I will discuss, it's a nice bridge to my story actually. Foiling with such a boat is quite hard, especially when you want to do it electronically. For now we want to look at a straight flying boat. Especially since we have flap design front wings, which in a sense limit us for controls. But you can imagine that as all the wings are connected to the same body, there are three types of outputs which we're interested in, which is the rolling motion of the boat, the pitch, and the height of the boat, the altitude for a plane. And we have both left and right flaps and the back wing as an input. So you already have a 3x3 multiple input, multiple output system. But as they're all coupled, as they're connected to the same body, it gives a lot of issues for the controller. As one wing moves up, the other moves down. If the back wing moves up, both front wings move down, as the pivot point is the center of gravity. So we can use some mathematics to find the right control pairs, which we have done. And we can use these control pairs to then decouple the model into more simple single input, single output control schemes. Which leads us to my next slide. For the roll control, we can use both front foils in opposite direction and both foils at the same time for the height control. And we can use just the back wing because it generates a lot of lift because it was designed 2 years ago when the boat was a little heavier. And we can use it solely for pitch control. And we can add them all together. So we have, for the left flap, we have the PID controller from the height plus the PID controller for the roll. For the right flap, we have the PID controller for the height minus the PID controller for the roll. And the back wing kind of speaks for itself. Of course, this is all very interesting in theory, but making the translation to a real-world system is quite difficult, I must say. So we have a few sensors. We have the surface probes, or floaters as we call them, which measure the height of the boat above the water. And we have an X-Sense IMU, which measures the orientation of the boat, but also all accelerations around every axis and Cartesian coordinates, and the velocity of the boat through the water. You can imagine that some of these sensors are quite noisy, and you need to filter them correctly to get the right data for the control system.
Are they gyros or the accelerometers?
We have prefused gyroscope data. So the roll and pitch signal are quite stable, yes. But for the height of the boat, for planes they use the accelerometer and a barometer, which they combine. So they have a good signal for that, because the accelerometer, if you integrate it twice, you also integrate the noise. So that signal kind of like goes out over time.
But the accelerometer is only to the roll and pitch.
No, you can use the accelerometer for different things as well. For the gyro, you use a gyroscope and the accelerometer, and then combine those so you have a better roll signal. But for the height, we use the more noisy surface probes and the accelerometer together to have a more stable signal. So, any questions so far? Yes?
Is your canal configuration inherently stable?
Nope.
No.
No, a canal configuration is not inherently stable. And also this inverse one is not stable as well, because that center of gravity is in between the two foil areas. And yeah, therefore we can have more aggressive steering. But yeah, downside of course we are not stable yet.
Yes.
Yeah.
Is it something you want to do, like have a stable boat?
Well, when I came here in the beginning of the year, I was really looking into that, and I would like to. But as I already said as well, you lose a couple of percentages in your efficiency, because all the downforce that you create with your back tail, that is lost, and you don't want that.
The canal configuration can be stable, right?
It can be stable, but you have to indeed really look. Also have a kind of high of aspect ratio, because that stability comes with other problems as well. Yeah. Well, if you have that front wing, which is for us the back wing, if you don't make it high enough, you have stall problems, and that could be also a problem at our boat. But therefore, we still keep it at this. If this works really well, yeah, maybe that could be a really nice idea.
Yes. Okay. So we have prepared 2 demos. Which is quite nice for you to see. First of all, we would like you to see, come to the boat and look at us to the motion of the front wings. So you can see the whole mechanism Camille talked about before. So you could come look at it with us. I think. Yeah, it lost the internet.
In the meantime, we could also do the startup sequence maybe.
Yeah.
So before we start testing, we always want to do a test if all the motors work. And that can be done with a startup sequence that we programmed to see if we can reach all maximum angles of attack and flap angles. Kan nu gewoon?
No, wait.
Oh. We have to wait a little bit.
Yeah, now you can.
Yeah.
Yeah.
You can see over here the first one, the second one, and now at the back.
As you can see, the back wing is quite slow, but luckily it only needs very slight adjustments when we are actually foiling. And also, which is our other demo, yes. So we have since we have an electronic system, we can also emulate like mechanically coupled system, which is just a P controller with a very high gain. So if the float goes up, the wing goes down. If the float goes down, the wing goes up. And as it goes over the water surface, it will self-stabilize around the good wing angle.
And that's the nice thing about electronically, like if you have problems with waves and it will jump up a lot, like the mechanical system has of course its own damping, but you can't change anything about it. And
Yes.
the thing we can do is, for instance, putting on low pass filters on it.
Yes, it gives us a lot more flexibility for this system. Yeah. So let's see if I still had another slide.
Of course, in the later on
Really?
in the drink we can tell you a lot more about it.
Yeah.
But let's finish it off, I think.
Yeah, let's finish it off.
This sensor here, is that a
Rotary encoder, digital rotary encoder. Yeah. So where does this P controller leave us? Well, we tested that at the beginning of the year. Let's see. Yes, and it dives back into the water, which has to do with exactly what I started talking about at the beginning of this talk, which is that our flaps have a very limited motion. So we need to use both foils at different angles to stabilize the roll. So that's what we're going to test hopefully next week.
Yeah.
Right?
Yeah.
So, oh, not again. So, what's next? Apart from our basis model, we would like to use that basis model to create more robust model-based controllers, so they are less prone to errors caused by slight changes to the system. You can imagine that if we change the center of mass a little bit, the controller needs to either be retuned or it should be robust for that. And we also want to use measurement data in combination with our basis model to make a better estimation of the flight dynamics, since the hydrodynamic coefficients we get from the hydrofoils mechanics subteam does not necessarily mean it matches with reality. So again, modeling errors slip in very easily for a system such as ours. So, which leads us to our goal, foiling in more rough waters, as we could see in Monaco. And that's it, I think.
Yeah.
Thank you.
Thanks a lot for listening.
I've got another question from the online viewer.
Yeah.
He asked if the use of a specific hull design, like a monotride cat, would be like meaningful or useful for the next time. I don't know what type of hull you guys use right now.
Well, I've heard about certain hulls that could make use of the ground effect, for instance, that you have more lift if you have a couple of centimeters or tens of centimeters across the water.
Mm-hmm.
That could be, of course, reason to use another hull. But what makes it, why we use this hull is that only the center part is in the water. And if we have the exact great weight, then only the sides, the buoys, that's how we call them, will only touch the water. So that's why we use this configuration, like we have this whole design.
Yes, but also making use of the ground effect doesn't really make sense for such a small boat.
No.
If you have waves which have quite a large amplitude, especially what we could see in Monaco, I mean, the races are not cancelled until the waves are half a meter high. So you can't really use the ground effect then, because the waves are going to touch the boat anyhow.
True.
And maybe when you're like driving, can it make a difference then? Like when you're not flying yet, but maybe if you can have like less drag where you're like not flying, but you're still like driving. That's how you call it, right? Get less drag from it. I don't know.
Yeah, but of course you could deviate in designs, also in catamaran design. You could also do that, but it has all kinds of things. You would have to change a lot in the current design we have, and we'd like to also optimize the design we had. Like this whole design is something that we are working on a couple of years now. But same as for the foils, we first want to see if this configuration works for us. And we want to get this really flying. And then we could also look at other things, also the offshore boats maybe, which are really huge and have way other configurations and struts that are like 2 meters high.
Yep.
That's
very limiting designing features are race in Akram, where the depth of the water is only 75 centimeters or so. So that's also the limitation of the length of our struts, because the boat can only go in that far. Yes.
For the transition from going like non-sailing to sailing, do you have some kind of like feed forward?
Yes, it's since we estimate that the motor of the boat can go quite quickly through the transition, we have that the boat generates no lift, so it remains in the water up to a certain speed. Then roll stabilization activates, so it gets into zero roll, and then when it goes 22 kilometers an hour, we have a transition to getting the boat up, and then the control system kicks in. So there's a transition scheme in between.
What kind of control do you use there? Is the PID controller for
Yes, it's a PID controller, yeah, for now at least, with partial feed forward, because the PID controller is works after gravity compensation. So if you have a state space system, you have some constants, and we remove the constants, and we have a formula for that, and that's used as a feed forward scheme.
So basically you feed forward your gravity as well.
Yes, yeah. Other questions?
Yes, good question about the future.
Yeah.
Where are you today, and where do you want to be in 2 years from now?
Depends also on what SIP system you ask this question.
Yes.
It depends on if you ask this to electronics or do you ask this question to the whole team.
The whole team.
The whole team. I think first, the stable foiling. It were our main goals: stable foiling, also being the fastest, but also being the most efficient. So winning the race for sprint, also winning for endurance. And what for me would be a goal, like for long-term planning, is having modular systems for your struts. So like being in Monaco with whole different struts, whole different wings, also being able to produce your own wings, so you can really test and swap out wings and struts. That would be really nice.
Yeah, and for control, a very large goal is that is to have a mathematical model of the boat, which is a good enough estimate so that during the winter some good estimations can be made on what kind of control scheme you want to use. Yep.
Oh, well, how about your budget? Are you budget limited?
Well, we can make more budget. Like it depends on us how much budget we have.
Do you have sponsors standing on the sideline?
Yeah, we have a lot of sponsors. We
Yes.
can't do this without sponsors, indeed.
No.
We can't do this without sponsors. It's impossible for
You
us.
can see the lots of stickers on the side of the
And
boat.
what do you say right now? You're limited. If there's not enough funds.
Well, what
I
we
don't
do?
feel limited.
No. Our policy is a bit like, if you want it, be sure that you're really in time with it and try to get sponsors for it. And I think 75% of the times people are willing to sponsor if you make them enthusiastic.
Or do you do it once in a while, every quarter? Do you do a dog and pony show? Or?
Well, we have communication, a whole other department for that. For instance, Sam, trying to get more sponsors. We do events like this to get people enthusiastic, and we also
have
I think we go to fairs.
partner events.
Yeah.
We have some fairs we go to indeed. In at the beginning of April, we have the Solar Solutions Fair, where with one of our partners, we will go there with our boat and talk about solar cells for 3 days. So that's quite nice. But we also have, of course, our boat reveal, where all of our sponsors will be. So there are many interactions.
The Solar Solutions Fair?
The Solar Solutions Fair is a fair in Haarlemmermeer, and it's for all solar companies. So last year we were there with our boat on ourselves, and we talked a lot with new companies to see if we could find new technologies to implement for our solar deck. But maybe some could also talk about that.
Yeah, so it's an expo for different solar cell techniques. So this is both on your roof, but also for these immense factory buildings. This every single bit of solar cell or solar panel technology that is there on the market will be there during the Solar Solutions Fair. And like Jitse said last time, we were there by ourselves. So we're mainly looking for new partners, new technologies that might be applicable for our own project. And this time in April we'll be together with our partner SolarStone, who builds systems to attach the solar panels to your roof. So that's also a thing that we do with our partners. It's not only we're nice and we have a great project, give us money. We also do things, of course, for them. One of those things is to be on the expo.
Yeah.
One more question on the continuity of the team.
Yeah.
Do you have a lot of turnover? People that leave the team or new ones come in?
Every year we start with an entirely new team, and there is a small, I believe, 2-week time period in which we transfer everything to the new team, and we try to document everything as we go through the year. We also work a lot on multiple year plans this year. We want to break through the year circle and have some projects which will take longer than just our year, but will continue into other teams' years.
I think it would also be nice to mention that we made use of feedback evenings.
Oh yeah.
Like every 2 weeks, almost all team members come over here and we discuss per sub-team what the ideas are. Can we make things better? What are those opinions? And we take that all into consideration. Which makes it, I think, a bit more better for continuity.
Yeah. It's easy to forget about the feedback evenings. Yeah, they're
true,
so obvious.
It's a lot of value.
Yeah,
It's
absolutely.
What about the spin-offs? Have you already seen some spin-offs out of this?
We have not. We don't have any spin-offs. No.
No, we discussed something about the backstrut, but we are not sure yet how to do that. We'd first like to see how everything behaves, of course,
Yes.
and see if those things can be produced on other scales than just one batch.
Of course, Delft has one spin-off. I believe it's called Flying Fish. But they started with Flying Fish after already having the team for 8-9 years, and we're still in the 6th year. So there's still some time of long-term plans rolling out.
Any bet already been applied for?
No, not yet.
Not yet.
Not yet. No.
Would you want to make a scale model of the boat to maybe get more accustomed to the dynamics of the boat?
Sorry?
To get accustomed to the dynamics of the boat, to make a scale model, because it's quite hard to test this, probably, right?
Yeah, true. Well, what we maybe you can tell more about it, but what also be a nice thing to do is maybe not making a real life model, but making a piece of software where pilots can train for the dynamics of the boat.
Okay,
And
yes.
that's a nice thing
now
to
I
talk
understand.
about.
Yeah. So if you have a good mathematical model of the boat, you could, for example, make a video game in which you could train the pilots, so they understand better what to do with the control system. Yeah.
Who are the pilots? Like, who is actually driving the boat? You?
Yes, me, and we have 3 more.
But you need a boat license? Or
Yes, yeah, you do, definitely. The boat goes faster than 25 kilometers an hour.
And how many horsepower?
How many?
Kilowatts or horsepower of motor?
7
We
kilowatts. around
have
that. I think it was like it's now limited at 7 kilowatts at sprint.
yes, peak output.
Yeah.
But
Yeah,
the
that's
motor
for
could
peak.
take more.
Yeah,
But
a lot more.
axles and the gears and such, which will be in the new struts, are so small
Yeah.
that we first want to test if they could actually hold it.
Everything is really tiny in our design. Like also the motor, we can show that as well. Motor is also for RC, for RC causes. But still, we can reach in theory 50 kilometers an hour because of our efficiency.
Rekenen we dan met 10 pk?
Dat
10
zou ik niet weten. Ja,
Like,
7
7
kilowattuur.
7 kilowatt.
Ja, 7 kilowatt.
Of 10 pk?
Okay,
Mm.
that could be the case.
Have you the maximum power that the solar panels can deliver?
And a sunny day in Monaco, it will be 1.5 kilowatts.
Yes.
Doing the endurance, for instance, takes us about 70% fully on solar power and only 30% on a battery.
Yeah.
Because you also get a battery, especially for sprint. It's almost impossible to sprint with only the solar power. So you use the battery as well. You are allowed to charge it up beforehand, and you make use of it to efficiently drain it off until you reach that 3 hours.
Yeah. It's
Yeah.
good to also remark that we have a very small battery of 1.5 kilowatt hours.
I've got another question from an online viewer. He says, Murphy's Law works always in these phases of design. Is
Yeah.
there a fallback for the controls?
Yes. Have good sensor data and then use the most basic of basic controller you can think of.
Also, being able to test.
Yes.
Yeah.
You can imagine that if you want to test the control system, everything about the boat needs to work reliably. So, in a sense, testing the control system is the ultimate test for the boat.
Yeah, the final test.
Yep.
Yeah.
Yep.
About data, like input data.
Can you speak a bit louder?
About your input data, how sensitive is the access?
How sensitive it is. The X-Sense is very accurate, I would say. We can take more data out if we want to. It can log data up to 100 Hertz, but we don't even use that much data because it will only overflow our communication lines. Let's see. So at least the roll and pitch signal from those I have calibrated, they are very stable. I still need to validate whether the speed signal is very stable, but I could filter it. It's no big deal. And we also still need to test the sensor fusion of the floats with the X-Sense. Yeah. So I can't really say anything about it yet.
Okay. If we don't have any questions, okay. Thank you very much.
One last remark, also for people at home. If one of you guys could switch to the next slide. There's one more. If you are interested in joining the team next year, we are currently... Yes. So if you are interested in joining the team for next year, we are currently recruiting new team members to start in September. Please do contact us. You can contact us on our website, solarboattwente.nl. You can also contact us on our social media. If you want to join the team, just go to our website solarboat20.nl/join. I think that's the last thing I would love to see. You need to be a student in Enschede, and you need to be motivated to do a lot and to be here every day to innovate.
And this is a mantelzorg.
I mean, for some people. no, it's
It's vrijwillig, no?
yes.
Yes.
It's all family prepared.
Yeah.
So I think that's it for the presentation part.
Ja. Kunnen wij nog even de componenten...
Zeker.
Ja,
zeker.
tuurlijk.
Of
course we can.
Tuurlijk.
There's a lot to talk about.
Ja.